Welcome to Cambridge Chemistry channel. Be sure to like the video and subscribe it. In this video I will discuss Feb March 2024 paper 429701. Let's start. I have solved this paper earlier. Now in this session I will discuss the answers because it's very lengthy paper. So for saving time I have this solved earlier. Potassium iodide, question number 1. Potassium iodide is used as a reagent in both inorganic and organic chemistry. Potassium iodide forms an ionic lattice that is soluble in water. Define enthalpy change of solution delta H SOL. Enthalpy change, it is enthalpy change when 1 mole of ionic solid is dissolved in excess amount of water to form infinite dilute solution under standard condition. Question number part 2. Potassium iodide has a high solubility in water, although its enthalpy change of solution is endothermic. Explain how this high solubility is possible. Potassium iodide forms bonds with water like ion dipole bond. In addition to this, hydration energy, enthalpy change of hydration, there are 2 points, 2 number. So enthalpy change of hydration is of potassium iodide is greater than lattice enthalpy change of lattice energy. So that's why this high solubility is possible. Table 1.1 shows Table 1.1 gives some data about the halide ions, chloride, bromide and iodide, and their potassium salts. Chloride is minus 364, minus 335, minus 239, similarly minus 70, 701, 670 and 629. We know that hydration is delta enthalpy change of lattice energy. This is lattice plus solution. Lattice energy plus enthalpy change of solution, and enthalpy change of solution is equal to enthalpy change of hydration and minus lattice energy. And you know that this is minus 364, minus 335, minus the difference between these two values is 29 and the difference between these two value is 41. This is 41, and similarly the difference between minus 701 minus 670 is 31 and 670 to 629 is 42. So the difference is almost same in decreasing level is same of both enthalpy change of hydration and enthalpy change of lattice energy. And look at this, if we solve hydration minus lattice energy, we have 337, 335 and 336. So explain the trend in the enthalpy change of hydration of the halide ions. Down the group we know that delta H hydration become less exothermic, size of anion is increased. Bond between iodide ion and H positive of water become weaker, that's why less energy is released. And another point is that the enthalpy change of difference of enthalpy change of hydration and enthalpy change of lattice energy is almost same. So these are the 2 points which you are supposed to write down. One is less exothermic, size of anion is increased, and bond between iodide and H positive ion. This is the ion dipole bond like this. Look at here, ion This is the ion dipole bond between on all sides of so this will become weaker as iodide ion is increased. The delta H solution values of these potassium halide are almost constant. Use delta H hydration and delta H lattice data in table 1.1 to suggest why. Because change of hydration and change of lattice, as I have earlier told you, discussed you that the difference between delta H hydration and delta H lattice energy down the group is almost same. So, because change of hydration and change of lattice energy nearly same from chloride to bromide, or difference of hydration and lattice energy is also nearly same. So, this is the reason. The enthalpy change of solution of potassium iodide is plus 21.0 kilojoule per mole. Use this information and the data in table 1.1 to calculate the enthalpy change of hydration of the potassium ion. Delta, we know that delta H hydration is enthalpy change of lattice energy, lattice energy plus enthalpy change of solution. So, we know that minus 629 in case of iodide, this is the enthalpy change of lattice energy, and enthalpy change of hydration of iodide is minus 330 minus 293, and this is we have to know, this is enthalpy change of hydration of potassium ion, or you can write down like this: enthalpy change of hydration of K positive ion plus minus 293, this is given in above table, and minus 629 plus 21.0 is the delta H solution. So, the answer is minus potassium enthalpy change of hydration of potassium ion is equal to minus 315 kilojoule per mole. Solid lead 2 iodide forms when potassium iodide is mixed with lead 2 ions. The solubility product Ksp of PbI2 is 7.1 into 10 raised per to minus 9 mole cube dm minus 9 at 25 degrees centigrade. Calculate the solubility in mole per dm cube. We know that lead 2 iodide is equal to lead 2 ion and 2 iodide ion, and where Ksp is equal to, we know that Ksp is equal to lead 2 ion and 2 iodide ion square. So, this is x2 positive plus 2x minus square. So, this is equal to 4x cube. 4x cube is equal to 7.1 into 10 raised per 2 minus 9. So, 4x cube is equal to 7.1 into 10 raised per 2 minus 9. So, x is equal to under cube is equal to, this is the answer, 1.2 into 10 raised per 2 minus 3 mole per dm cube. This is the solubility of lead 2 iodide. The ionic radius of lead 2 ion is 0.120 nanometer compared to 0.133 nanometer for potassium ion. Suggest how the enthalpy change of lattice of lead 2 iodide differ from the enthalpy change lattice of potassium iodide. Explain your answer. Lattice energy of lead 2 iodide is greater. Lead 2 iodide is greater than potassium iodide because this is suggest how, this is suggest. The first statement is that lattice energy of lead 2 iodide is greater than potassium iodide because size of lead 2 ion is smaller than potassium, and lead 2 has more charge than potassium. Strong electrostatic force of attraction between lead 2 ions and iodide ion, hence a large amount of energy is needed to break this lattice. So this is the in context of this, the ionic radius is 0.120 and this is 0.133. The size is smaller but charge is greater, so that's why lattice energy of lead 2 iodide is greater than potassium iodide. Part C is potassium iodide slowly oxidizes in air forming iodine. Reaction 1 is this, and table 1.2 shows some data relevant to this question. Enthalpy change is minus 203.4 kilojoule. So these are the enthalpy standard entropy. So this is the entropy, delta S entropy is equal to sum of delta S entropy of product minus sum of delta S of reactant. So 2 into 155.5 plus 2 into iodine 116.1 minus 4 into 106 point, this is potassium iodide. In case of potassium iodide, 4 into 106.3 plus 205 oxygen is 205 106 is this, and 205.2 is the, and 2 into 213 for carbon dioxide, 13.6, sorry, plus 205.2 and plus 2 into 213.6. So this is equal to minus 514.4 joule K inverse 1 mole inverse 1. So when we subtract product minus reactant, we get entropy change is 514.4. Use your answer to C1 to show that reaction 1 is spontaneous at 298 Kelvin. So delta G is equal to delta H minus T delta S. We have delta H is equal to minus 203.4. This is 203.4 minus 298, and this is the entropy 514.4 divided by 1000. This is equal to minus 50.1 kilojoule per mole. The group 1 carbonates are much more thermally stable than group 2 carbonates. State and explain the trend in the thermal stability of the group 2 carbonates. Down the group thermal stability increases because size increases and polarizing power of cation decreases. And if polarizing power of cation decreases, distortion of anion decreases, so more energy is required to decompose group 2 carbonates. A student electrolyzes a solution of potassium iodide for 8 minutes using a direct current. The half equation for the reaction that occurs at the anode is given. So this is equation. Write a half equation for the reaction that occurs at the cathode. This is the half equation. You know, potassium iodide is solution, aqueous solution. So this is reaction at cathode, hydrogen ion instead of potassium, because potassium is above in the reactivity series than hydrogen ion. So hydrogen ion discharge at cathode to form hydrogen gas. After the electrolysis, the iodine produced requires 21.35 centimeter cube of 0.100 mole per dm cube sodium thiosulfate to react completely. So this is the reaction. Calculate the average current used in 8 minutes during the electrolysis. So this is the sodium thiosulfate. First calculate the mole of sodium thiosulfate. So this is mole of 0 point concentration into volume over in centimeter cube divided by 1000. So this is the formula to calculate the mole of sodium thiosulfate. 0.100 into 21.35 divided by 1000. So we get mole 2.135 into 10 raised power to minus 3. So by using mole ratio we get mole of iodine. So 2:1 to 2.135 ratio x, and mole of iodine is 1.068 into 10 raised power to minus 3. So this is step 2. This is now step 3. We know that 2 iodide ion, this is the reaction at anode. 2 iodide ion gives iodine plus 2 electrons. So 1 ratio 2 electron, 1 iodine ratio 2 electron. This is iodine moles. 1 mole required 2 Faradays. And what would be the Faradays if 1.068 into 10 raised power to minus 3 mole is there? So x is equal to 2.135 into 10 raised power to minus 3 Faradays, and we know that 1 Faraday is equal to 96,500 Coulomb. So this is the Coulomb, and x is equal to, what would be the Coulomb when 2.135 into 10 raised power to minus 3 Faraday current pass. So x is equal to 206.0, and now current I is equal to Q upon T, and this is equal to 206.0 divided by 8 minutes time is given. So 8 into 60, so the answer is 0.429 ampere. Hopefully you understand, and please follow the same pattern, because this is 2024 Feb March paper. The same pattern is given to you in 2024 hopefully, and you know all topics are assessed in the lattice energy, starting from enthalpy change, then lattice energy, entropy, then electrochemistry, organic chemistry. Potassium iodide is used as a source of iodide ions in organic synthesis. One example of this is shown in the synthetic route in 1.1. Benzene is changed into nitrobenzene, and you know that for this reaction the reagents are concentrated nitric acid, concentrated sulfuric acid, and temperature is you can write down 55 degrees centigrade, but because mostly in mark scheme 55 degrees centigrade is written, but you can write down 50 to 60 degrees centigrade or 50 to 60 degrees centigrade. So the reaction is nitration, but the type of reaction is electrophilic substitution. So now next nitrobenzene changes into phenylamine, and phenylamine, because this is a reduction reaction, hydrogen is gained by this compound, and these are the reagent, tin plus HCl concentrated and heat under reflux, and nitrobenzene changes into phenylamine. So this is a reduction reaction, and phenylamine changes into diazonium chloride. So the reagents are NaNO2 and HCl, and this reaction is diazotization, and HCl dilute is used at 5 degrees centigrade. So this compound is formed, diazonium chloride. Now over here iodobenzene, you know that this is nucleophilic substitution, type of nucleophilic substitution, but we cannot say this is nucleophilic substitution. This is iodide is this bond is broken over here. The curly arrows are showing that iodide ion is substituted over here, but this is addition, and from here nitrogen is eliminated in this reaction. You can say this reaction is addition elimination reaction. And plus nitrogen is, and heating, on heating it gives product E. Identify the reagents required for step 1, 2 as I have discussed earlier, the concentrated nitric acid and concentrated sulfuric acid. And step 2, this is reduction reaction, and in this tin plus HCl dilute and heat under reflux. Step 3 occurs in 2 stages. NaNO2 HCl undergoes an acid base reaction to produce HNO2. HNO2 react with C6H5NH2 to produce DC6H5N2+. So this completes the equation for stage 1 and stage 2. NaNO2 to form HCl plus HCl to form HNO2 and N plus NaCl, and HNO2 plus HCl write down like which is given by the examiner, C6H5NH2, and this is produced, this is changes into C6H5N2. you can write down Cl as well, and 2 water molecules are formed. The iodide from potassium iodide react with the D in step 4. The mechanism is shown in figure 1.1. Look at above reaction, beta, look at here. These are the 2 hydrogen molecules which are eliminated, and these are the N joined over here, and these are 2 water hydrogen. So, and O2. So 2 water molecules are formed, so this reaction is balanced. The iodide from potassium iodide react with D in step 4. The mechanism is shown in figure 1.1. Suggest the name for this mechanism. This is addition elimination reaction. So very lengthy question carrying 26 marks, and almost all topics are assessed in this question. Please follow the same pattern and solve this paper, or rather watch this video very carefully. Question number 2. Question number 2. Water is an amphoteric compound that also acts as a good solvent of polar and ionic compound. Equation 1 shows water acting as a Bronsted-Lowry acid. Equation 1, H2O plus nitrogen dioxide to form HNO2 hydrogen nitride plus OH negative. Identify the 2 conjugate acid base pairs in equation 1. Acid 1 is here it is the acid because it is proton donor and it is proton acceptor. So acid 1 is water, and conjugate base of acid 1 is OH negative. This is conjugate base, this is conjugate acid, and this is acid, and this is base, because this is proton acceptor, this is proton donor. Proton donor is an acid and proton acceptor is a base. And over here this is conjugate acid, this is the conjugate acid of this base, and this is conjugate base of this acid. So HNO2 is acid 2 and conjugate base of acid 2 is nitrite ion. Water also behave as Bronsted acid, Bronsted-Lowry acid when it dissolves CH3NH2. Explain the ability of CH3NH2 to act as a base. This is proton acceptor. Write an equation to show water acting as a base with CH3COOH. Water accept proton, so that's why water acting as a base. So this is acid and this is water. So ethanoate ion and hydronium ions are formed. So that's why this is water except proton. The ionic product of water Kw measures the extent to which water dissociates. Water is to form H positive and OH negative. Shows figure 2.1 shows the how Kw varies with the temperature. So this is the graph. This is Kw over here, and this is temperature. So write an expression for Kw. Kw is equal to H plus OH negative. Use information from 2.1 to deduce whether the dissociation of water is an exothermic or endothermic. Explain your answer. This is exothermic as the value of Kw increases with increasing temperature. All case, you know that all case are temperature dependent. So by increasing temperature, Kw is going to increase. So look at here, by increasing temperature, Kw is going to increase. An aqueous solution has pH is equal to 7 at 30 degrees centigrade. So H positive ion. Use information from figure 2.1 to explain why this solution can be considered to be alkaline at 30 degrees centigrade. So this is H positive ion, this is pH, and H positive ion is equal to 10 raised to minus pH. So 10 raised to minus 7 is equal to 1.5 concentration. H positive is equal to 10 raised to minus 10 raised to minus 7. So H positive is equal to 10 raised to minus pH. So this is 10 raised to minus 7 pH. So which is equal to 1.5 into 10 raised to 2. So Kw is equal to 1.5 into 10 raised to minus 14. This is Kw 10 raised to minus 14. So 1.5 into 10 raised to minus 14 is equal to 10 raised to minus 7. That H positive value is 10 raised to minus 7 into OH negative. So OH negative is equal to 1.5 into 10 raised to minus 14 over 10 raised to minus 7. So this is equal to 10 raised to minus 7, 1.5 into 10 raised to minus 7. So POH is equal to minus log 1.5 into 10 raised to minus 7. This is equal to 6.82. pH is equal to, so we know that pH POH, sorry, this is POH, this is, we have pH, sorry, pH is equal to 14 is the Kw and minus 6.82, this is the POH, and the pH is equal to 7.7, which is alkaline. Question number part C, the three typical states of water have different standard entropies associated with them. Table 2.1 shows these entropies values. So plus 48, plus 70.1 and plus 188.7. Explain the difference in entropy value of water and solid and liquid. In solid, particles are orderly arranged. But in while in water liquid, water liquid is of disorderedness. So that's why this is the reason of the difference in the entropy value of water solid and water liquid. Explain why the increase in entropy is much greater when water boils than when it melts. In gases there is less intermolecular forces, so more disorderedness, more entropy, as gases are more energetic than liquid. So this is the reason. The energy changes for water to water liquid, water solid to water liquid are shown. Delta G is equal to 0.00, delta H is is plus 6.03 kilojoule per mole. So this is entropy is equal to entropy delta S, entropy of product, delta S entropy of the reactant. So 70.1 is equal to minus 48. So this is equal to 22.1 joule Kelvin. So by dividing 1000 we get 22.1 kilojoule mole inverse 1. So this is delta G is 0 is equal to delta H 6.03 minus T into 22.1 into 10 raised power to minus 3. So T is equal to 6.03 over 22.1 into 10 raised power to minus 3, which is equal to 272.85. So approximately this is 273 Kelvin. So we know degree centigrade is equal to Kelvin minus 273. So 273 Kelvin value is 273 minus 273 is equal to 0 degree centigrade. Metal air batteries are electrochemical cells that generate electrical energy from the reaction of metal anodes with air. The standard electrode potentials for zinc air battery are shown. Zinc hydroxide plus electron, 2 electrons to form tetrahydride. This is the complex ion, complex compound, 2 electron to form zinc plus 4 OH negative. This is E naught of minus 1.22, and this is reaction at anodes plus 0.40. This is more positive, this is less negative. So this is reduced value and this is oxidized value. So E cell, we know that E cell is equal to E reduced minus E oxidized minus E oxidized. So this is equal to 0.40 minus 1.22, so which is equal to 1.62 volt. The zinc air batteries usually operates at pH 11 and 298 Kelvin. The overall cell potential is dependent on OH negative. The Nernst equation shows how the electrode potential at the cathode changes with OH negative. 0.40 minus 0.059 over Z log OH minus twice. So 0.5. So we know that pH is 14. Total pH is, and we have 11 at pH 11. So 14 minus 11 is equal to 3, and OH is equal to 10 raised power 2 minus 3 POH. So this is log 10 raised power 2 minus 3 square. So this is equal to 0.1345. So the 0.1345 volt is the energy. Iron is a transition element, pH 11. So total pH we know that is equal to 14. So OH pH is equal to like this, 14 minus 11 is equal to 3. So OH value is 10 raised power 2 minus 3, which is used over here. Iron is a question number 3. Iron is a transition metal in group 8. Again transition metal question. Iron is a transition metal in group 8 of the periodic tables. Please do focus on transition metals. Look at here, 2 questions from the transition metal. Iron is 2 questions. This is one question and this is another question. Look at here. This is another question from transition metals. This is about 14 marks. And next question is about 27 marks question, weightage for transition elements in this paper. Okay. Question number 3, iron is a transition metal in group 8 of the periodic table. Explain why iron has a variable oxidation state. Iron has, we know that transition metal has incomplete d orbital, so that's why they have variable oxidation states. Iron has incomplete d orbitals electrons, so d orbitals, so electrons are easily lost or gained from the incomplete d orbitals. Complete the shorthand electronic configuration of Fe and Fe3 plus. So this is orgon mean, said that we supposed to start from the fourth shell. So this is the electronic configuration till third shell. So now we supposed to write down the fourth shell electronic configuration of iron. This is 4s2 and 3d6, and for iron this is 3d5. 3 electrons are lost, 2 electrons from the s shell and 1 electron from the 3d orbital. So the 3d5 for iron 3 plus. An aqueous solution of F iron 3 nitrate contains the complex iron hexahydrate iron 3 plus. When solution KSCN, potassium sulfocyanide, thiocyanate and iron hexa Fe H2O6 3 plus are mixed, the color change is observed. The red complex, this is formed, this is the product form. Define complex. A complex in which central metal atom or ion forms dative bond with one or more than one ligands, with one or more than one ligand. State the coordination number of this compound. So there are 6 over here, 6 molecules of water form dative bond with iron, this metal ion. So the coordination number depends on the number of dative bonds formed by the ligand. So this is 6 written over here. So the coordination number is 6. The HOH bond angle in water is 104.5. Suggest the HOH bond angle in this 107, because water in complex ion has 3 bond pairs and 1 lone pair, you know, like this. Iron, sorry, this is, look at here, dative bond O and H, 1 lone pair is this. So that's why 107 is the angle, because water in complex has 3 bond pairs. So this is 1, 2, 3 and 1 lone pair. See, this is the bond which is dative bond, which formed with this central metal ion, and 1 lone pair and 3 bond pair. So that's why we know that bond pair lone pair is repulsion is more than bond pair. So in this way bond angle is 107. Explain why iron complexes are colored. This is a very common question of the transition metals and very important rather. D orbitals of iron split into 2 degenerate orbitals. 2 you can write down 2 degenerate orbital, non-degenerate orbital, non-degenerate orbital due to ligands and metal electron repulsion. Lower energy electron absorb energy from photon, which is equal to delta E, and delta E is different for different colored complexes and promoted to higher energy d orbitals. Electron absorb energy which is equal to delta E. So when electrons return back, emit radiations in the visible range, emitted energy wavelength is complementary absorbed radiation. Emitted energy and its complementary absorb energy. So these are the points which you have to write down in this question. So iron split into 2 non-degenerate orbital. So due to the ligand and metal electron repulsion, lower energy electron absorb energy from photon or light, which is known as light. Photon is the packet of light. Part 5, aqueous solution of complexes, and this complex and this complex are different colors. Explain why these complexes are different colors. Because both complexes absorb different energy gaps, because ligands are different, there is water as well as supercyanide ion is there. So that's why ligands are different, so the energy absorbed by the ligands also different. Both complexes have different energy gap delta E due to different ligands, and different frequency of photon is required to promote the lower energy electrons. So that's why they have different colors. Table 3.1 gives values for the stability constant of different complexes of iron. This is one complex, these are the two complexes whose stability constant is 5.90 into 10 raised to 1, and stability constant of this compound is this. These compounds can form when phosphoric acid react with iron hexa aqua iron 3 ions. So write an equation. So this can be formed. So these are two reactants. When they react with each other, this compound is formed. So iron, so say 3 plus H3PO4 to form iron H2O, 5 H2PO4, 2 plus hydronium ion. So this changes from 3 plus to 2 plus, H3O positive phosphate over here, and now reaction is balanced. So K write an expression for K step and give its unit. So this is the H2O5. So KSCN react with this complex to form this complex, and plus water. So this is the product. K step is equal to product over reactant. H2O So charge is +2 and water is formed. So while writing case tab expression, water is in large amount. Water is in large amount. So we ignore this. Just ignore this in this expression. So this is how to write down this expression, product O upon reactant. So the unit is so how to derive the unit? We know that the concentration, this is equal to mole dm inverse cube divided by mole dm inverse cube mole dm inverse cube. So this will be equal to 1 over mole dm inverse cube. The unit is mole inverse 1 dm cube. Now use the stability constant data in table 3.1. Calculate the value of the equilibrium constant Kc for the following equilibrium. So this is K2, this is K2. KSCN and H2PO4 and this is product. You know, this is the value 1.30 of this value H2OP5. So it means this is let's say that this is K2, K and this is K1. So we have 1.30 over 5.90 because K1 is the reactant. 1.30 into 10 raised to 2 divided by 5.90 into 10 raised to 1. So the answer is 2.20. And please keep it in mind, higher K step value always become product. Higher K step value always become product. So this is the case C. Now next question is question number 4. Ruthenium and osmium are transition metals below iron in group 8 of the periodic table. This is ruthenium and this is osmium. Osmium symbol is OS and RH is the ruthenium. Two different complexes X and Y can form when anhydrous ruthenium chloride RuCl3 react with water. So this is when react with water, this is a compound, and with water under certain condition. X and Y have octahedral geometry. Aqueous sample of X and Y react separately with excess of AgNO3. Different amount of AgCl are precipitated. So this is these two products are formed when it is precipitated, Cl2 positive and Cl plus. 1 mole of complex ion X produces 2 moles of AgCl and 1 mole of complex ion produces 1 mole of AgCl. Complete 4.1 to suggest formula for X and Y. So these are this is the product, this is the, and this is two products are formed. One is this Cl2 with Cl2 and this is plus 1. Formula of the complex Cl with 1 Cl and with 2 Cl. So this is the charge. Both complexes react with an excess of bipyridine BP. This is bipyridine. And please keep it in mind that this nitrogen has lone pair. This is known as BP. Octahedral, this is 3, and you know that 2 lone pairs with nitrogen so form octahedral, and octahedral, which is optical isomers of each other. Bipyridine is a bidentate ligand. Draw 3-dimensional diagrams of the 2 stereoisomers of RuBP thrice and 3 plus. So use this symbol to present the BP ligands. So this is the 3-dimensional structure. This is 3-dimensional structure. You can draw like this. On here, this is wedge, solid wedge, and this is dotted line, and these compounds, and these two are optical isomers of each other, mirror image of each other. Figure 4.1 shows another ruthenium complex. This is another ruthenium complex. The complex contains the neutral ligand pyrazine. Suggest how pyrazine is able to bond to 2 separate ruthenium ions, as it has 2 lone pairs form 2 dative bonds. Pyrazine is an aromatic compound. The bonding and structure of pyrazine is similar to that of benzene. Describe and explain the shape of pyrazine. In your answer, include the hybridization of nitrogen and carbon atoms, how orbital overlaps form pi bonds between the atoms in the ring. Each carbon and nitrogen atom are sp2 hybridized geometry. Sp2 hybridized geometry is planar, angle is 120, and pyrazine has a alternate system of pi bond formed by the lateral overlapping of p orbitals. So next question is, next part is predict the number of peaks seen in the carbon 13 NMR spectrum of pyrazine. You know that this is carbon, same environment of this and same environment of this, so that's why we have only one peak in carbon 13 NMR spectrum of pyrazine, because all have the same environment. Carbon atoms have the same environment, so that's why all carbon atoms are sp2 hybridized and have same chemical environment, so they have only one peak in C13 NMR spectrum of pyrazine. The overall charge of the ruthenium complex in figure +5. Deduce the possible oxidation state of the 2 ruthenium ions in the complex. It can be +1, +2 and +3. +1, +2 and +3. Yes, it can be +1, +2 and +3. Osmium tetroxide reacts with alkenes in a similar manner to cold dilute acidified potassium manganate. So with cold dilute acidified potassium manganate, we know that diols are formed. So this is HOC, COOH. So and PCl5 and react with PCl5 at room temperature, this compound is formed, COCl and SClOC. So step 3, this is osmium tetroxide, just like manganate ions. Please read the question very carefully. This is like the behave like cold dilute acidified potassium manganate. So cold, like this is similar behavior. Step 2, and we have OH over here in the products. we get OH and OH, 2O diol. Suggest the reagent step 1 is PCl5 or SOCl2. Draw the structure of exactly one repeat unit of condensation polymer G. The ester linkages should be shown fully displayed. So G, we know that this compound formed like this. OH, OH. And you know that this is ester. Condensation polymer of G is the ester. Like look at here, OH from this compound and H from this and OH from this compound. Similarly, sorry, not to react with this, it should react with this compound. This is Cl over here and HC, and this is Cl and this H from this side. So draw the structure exactly one repeat unit of condensation polymer G, the ester linkages. Look at this compound. This compound react with this compound. We have this compound diol and Cl, this compound is. So Cl from this OH, H from this Cl, we have this linkage C double bond O, then C double bond O. This is going to remove O by joining this O, and this is one repeat unit and this is another repeat unit. This is C double bond O, again repeat the same. This is again O, like this. This is full 2 repeat units like this. Hopefully you understand this question. If compound Q can be synthesized from the chlorobenzene in 7 steps using the route shown in chlorobenzene, CH3, AlCl3, and say this is electrophilic substitution, and this is also known as alkylation because alkyl is formed. Now oxygen, step 2, oxidize this compound to form CHO and oxidation to form this compound CnCHO, and we know that HCN and KCN nucleophilic addition, and this compound is and when carbon react with Cn and OH bond, this is known as cyanohydrin. This name is known as cyanohydrin. This part is same, nothing is changed with this, and this part is going to change. HCN and KCN to form cyanohydrin, and this is nucleophilic addition. Now acid hydrolysis, because COH is formed over here, this is going to hydrolyzed in the presence of acid to form COH and OH, and this is remain the same. And this CH3OH when react with this compound to form ester. This is the ester, but don't write this reaction is esterification. This is just write down condensation. Don't write esterification. So CH3OH, we can join this carboxylic acid with this, and now this is OH, and when react with SOCl2, this is secondary alcohol, and it is going to change with Cl when react with SOCl2. Now this is going to change over here, so this group is changed in the presence of SOCl2. So next, this reactant react with this compound, and potassium carbonate is also, and aqueous potassium carbonate. So this is again ClCOCH3. Cl is going to eliminate, and this H is also eliminate, CN, wide linkage, COCH3, K2CO3, and rest is same. Write an equation for the formation of the electrophile for step 1, CH3Cl plus AlCl3 to form AlCl4 minus CH3 plus. Complete the mechanism in figure 5.2 for step 1, the alkylation of chlorobenzene. Include all relevant curly arrows and charges. Draw the structure of the intermediate CH3, and this is the intermediate. Don't show this curly arrow, please avoid this. I just figure out this reaction, but you are not supposed to draw this arrow. So this is actually, this is like this, okay, but you are not supposed to draw this. Now hydrogen ion is going to separate. Step 2 is an oxidation reaction. Construct an equation for the reaction in step 2. This is step 2, oxidation reaction, and C7CH7Cl plus oxygen to form this compound. Suggest reagent for conversion of K to M in stage 3 and 4. You know that this is CHO aldehyde, and this is changed into CCNOH. It means HCN and KCN reagents are used, and heat under reflux. Step 4, H positive aqueous cyanide ion is this is going to changes into carboxylic acid. So this is acid hydrolysis, H positive, and water and heat. Identify the type of reaction that occurs in step 5. This is step 5, where condensation takes place, ester is formed, and please write on condensation reaction. Condensation, don't go for esterification, condensation or elimination. So step 7 takes place when P is heated with a weak base such as potassium carbonate. So when it reacts with the, in the presence it reacts with weak base and this reactant, what is formed, this compound is, this act as a weak alkaline solution. All carbonate solutions act as a weak alkaline solution. Suggest why a strong base such as sodium hydroxide is not used for this reaction. If strong sodium hydroxide is used, it can hydrolyze ester and amide. Okay, so that's why we can't use strong base over here. Q is optically active. Explain the meaning of optically active. Compounds contain chiral carbon. chiral carbon is that carbon which is surrounded by 4 different groups and which can rotate plane polarized light. Give 2 reasons why it might be desirable to synthesize a single optical isomer of Q for used as a drug. So minimum side effect and should be cost effective because 2 products are formed, and to reduce dosage, give 2 reasons why it might be desirable to synthesize a single optical isomer of Q for use as a drug. So it has minimum side effect, cost effective. Instead of forming 2, only 1 product is formed to reduce dosage. Next, Q is commonly used in conjunction with aspirin. Aspirin is a weak Bronsted Lowry acid because this is proton donor. pKa of aspirin is 3.49. 75 milligram of aspirin dissolves in water to form 100 centimeter cube of aqueous solution. Calculate the pH of this solution. 1 milligram, you know that this is equal to 0.001 gram, and 75 milligram, what would be the 75? This is equal to 0.075. So mole of aspirin is equal to 0.075 divided by 180 is the mass MR of aspirin. So the mole is 4.167 into 10 raised power to minus 4. We know that 100 centimeter cube has 4.167 into 10 raised power to minus 4 mole. So what would be the mole in 1000 centimeter cube? So aspirin has a mole 4.167 into 10 raised power to the minus 3 in 1 dm cube. pK is equal to, we know that this is the formula of pK is equal to minus log Ka, and Ka value is 3.236 into 10 raised power 2. This is the pK of 3.49. So 10 raised power 2 minus 3.49, which is equal to 3.236 into 10 raised power 2 minus 4. So now pH is equal to minus log under root into 4.16 into 10 raised power 2 minus 3. So we have pH is equal to this is the concentration of aspirin, and this is the pH. pK, the pH is equal to 2.936, which is 2.94, approximate 3 pH. Aspirin undergoes acid hydrolysis in the stomach. Give the structure of the organic products of this acid hydrolysis. Aspirin, acid hydrolysis. What is, where is aspirin? This is aspirin. So acid hydrolysis, this is ester, going to change over here. This is an acid, CH3COOH, and this should be H. The this is answer. These are the 2 products formed. So draw a skeletal formula of this compound CH3COOH, because he draw skeletal over here. So just draw the skeletal formula. Question number 6. Amino acids are molecules that contain NH2 and COH functional groups. Glycine is the simplest stable amino acid. The isoelectric point of glycine is 6.2. Define isoelectric point, the point in which no net electrical charge exists. No net charge exists because one carboxylic acid is there and one amino group is there. So that's why minus positive charge are cancelled out. So that's why this is isoelectric point when one carboxylic acid and one amino group is present. So the isoelectric point is the point in which no net electrical charge exists. Draw the structure of glycine at pH 6. So this is a pH 4, and this is ammonia, and this is proton acceptor. So that's why this is the structure of at pH 4. Figure 6.1 shows two syntheses starting with glycine. Okay, C2H5Br and COHH2. This is N C2H5, two syntheses starting with glycine. This is C, this is C, this is C. Reaction 2, it is going to react with this compound, reaction 2. So this is going to reduced and such compound bond with amide linkage. This react with this compound. Each this side react with this side, one H and one Cl to form HCl, and such compound is formed. An excess of lithium aluminum hydride, this is going to reduced to form CH2, hydrogen, loss of oxygen, and over here CH2 is formed. So NH and CH2OH, this is also going to reduce. This is carboxylic acid in the presence of lithium aluminum tetrahydride. This changes into primary alcohol. State the essential conditions for reaction 1. Heat under pressure, ethanol, reaction 1. Ethanol, and in the presence of ethanol and heat under pressure, 2 molecules of ethanol. So, or heat under reflux. Heat under pressure. Identify the reagents used in 2. This is the reagent used in 2 because this compound react with this compound. This is the reagent. Over here nucleophilic substitution SN reaction. Draw the structure of the organic product U that forms when boric and acid react with an excess of lithium aluminum tetrahydride. This is compound formed. This used as a reducing agent, reduced C double bond O into CH2, and this is carboxylic acid also going to reduce. A molecule phenylalanine R can react with a molecule of glycine to form 2 dipeptide S and T. S and T are structural isomers. So dipeptide bonds are formed. So one time COH react with this and H2N react with this. So this is dipeptide. Draw the structure of these dipeptides. The dipeptide bond form should be shown fully displayed. This is one type of dipeptide when this H2N react with this COH. No. This H2N react with this COH. Okay, rest of the structure is same. H2N, C double bond O, and OH from here, H from here. So this is elimination of water. So rest compounds are linked, like this is the amide linkage, and rest compound is same. Now in this phase, this carboxylic acid should remain the same, this carboxylic acid should remain the same, and this carboxylic acid react with this amine group, and H2N similarly just rotate this compound. H2N is the same, and C double bond O NH, this is NH, and this COH remain the same, and this is attached with this benzene ring. So these are two, the peptide bonds formed should be, these two peptide bonds are formed. This is S and this is T. C part, a student proposes a synthesis of hippuric acid by the reaction of benzamide and chloroethanoic acid. The reaction does not work well because benzamide is a very weak base. Explain why amides are weaker bases than amine. This is benzamide and this is this reaction is going on. NH2 lone pair of nitrogen is delocalized with the pi bond of oxygen, so lone pair is not available for protonation. So that's why benzamide is a very weak base. Then chloroethanoic acid does not work because benzamide is a very weak base. The pKa of chloroethanoic acid is 2.86 and pKa of ethanoic acid is 4.76. The higher the pKa value, weaker the acid is, and lower the pKa value, stronger the acid is. The reason is this, that in chloroethanoic acid electronegative elements like chlorine is attached with this, which is electron withdrawing group and make OH bond weaker, so easily dissociate, hydrogen ion is easily dissociate, while 4.6 ethanoic acid CH3 is alkyl group which is electron donating group, so that's why OH bond becomes stronger, hence not easily dissociate. So that's why ethanoic acid is weaker acid than chloroethanoic acid. Explain the difference between these two pKa values. Lower the pKa value, stronger the acid is. Higher the pKa value, weaker the acid is. Hence ethanoic acid is weaker than chloroethanoic acid. As chlorine is more electronegative, it has a strong negative inductive effect, so easily ionized. The proton compound V is another amino acid. The proton H and MR spectrum of V shows hydrogen atom in 5 different environments, A, B, C, D and E as shown in figure. So A, B, C, D, E. C, D, this is surrounded by this and surrounded by this, and this is B. Chemical shift 9 to 13. Name of 9 to 13. This is RCOH, peak 9 to 13. This is RCOH, this is R and this is COH. So this is gives singlet peak because benzene give singlet, and 6 to 9 multiplet, 6 to 9. This is HAR, aryl group. This is aromatic ring, H with AR. So this is B peak, B peak is multiplet. So H environment is the benzene ring aryl. 6 to 9 is multiplet. 2.2 to 3.0. C is carbon on this environment CH2, and on this side many hydrogen are there. So if this is going to triplet, because 2 hydrogen surrounded by 2 hydrogen, 2 plus 1, n plus 1 number of carbon atom, and this is 1 is equal to 3, so gives triplet peak 3.2 to 4. 3.2 CH2n electronegative element on this side, and CH3 CH2 and CH on this side aryl group. So this is all shows 3.2 and 3.2 to 4. So this is triplet, and E, this is E surrounded by 2 hydrogen atoms. So nitrogen CH2 nitrogen, this is singlet peak 125.0 RNH alkyl NH. If alkyl amines are there, the peak is 1.5, and this is singlet because 1 NH2. Complete table. 1 point, this is NH2 CH2 next to amine, CH2 next to amine, basic RNH, this is alkyl next to this compound alkyl amine. This will give singlet peak because 1 hydrogen is there. So this will give singlet peak 1 to 5.0. Complete table 6.3 by placing tick to indicate any protons whose peaks are still present in the proton HNMR spectrum of V taken in D2O. D2O remove OH, remove AOH, DO2. So it will become invisible, and this is also become OD. So NH2 peak is invisible. So cross, this is E and A are invisible. Next take. So this is all about of this paper. Hopefully you understood, and if you like this video, please press the like button and subscribe the channel. Okay, Allah Hafiz. Good luck for exam.